Hello, my name is Kontoudis, and in this video I will present your work on online model-free motion planning in dynamic environments. The motivation of this work regards realistic motion planning, which takes into account kinodynamic constraints. We also consider temporal constraints, as in dynamic environments we need to navigate at specific time frames, which leads to finite horizon formulation. System dynamics are often difficult to derive and may change throughout the navigation. But even if we have the dynamics, it is computationally expensive to compute the optimal control, and therefore we cannot implement in real time the controller. We also consider communication and security aspects by communicating as little as possible, leading to an intermittent control formulation. The main idea of this paper is shown here. We define the continuous time Q function as the optimal value function, the intermittent Hamiltonian, and the time trigger Hamiltonian. Next, by doing some mathematical manipulation, we get the augmented representation of the Q function. Then we use some elements of the augmented Q matrix to reconstruct the intermittent controller, which is a function of the sample state. We employ an intermittent condition to close the loop, which is based on an inequality of the squared norm error gap. The main theorem of this paper shows that the origin is globally asymptotically stable equilibrium point of the closed-loop system under some inequality conditions. The proof is Lyapunov-based, and we consider both flow and jump dynamics. The steps that we follow are shown here. First, we compute a global path using the RRTX, which can be used in dynamic environments. Next, we execute the intermittent model-free optimal control, and we measure the kinodynamic distance. The kinodynamic distance is the distance of the straight line connecting the waypoints to the actual location of the robot. Next, we augment the obstacles based on the maximum occurred kinodynamic distance, and we replan with RRTX. Let's see how that works in practice. We can see the robot navigates. In white line, you see the global path. In red line, you see the traverse path. The obstacles are shown in blue, and they appear and disappear in an unpredictable fashion. In pink, you see the augmented obstacle space. On the right-hand side, you see the current kinodynamic distance, and on the left-hand side, you see the maximum kinodynamic distance, which we use to augment the obstacles. As you can see, the robot can navigate from a start state to a goal state using the intermittent optimal controller and RRTX. Our method is completely model-free. It works in an intermittent fashion. It operates in real time, and it is even applicable in dynamic environments. Thank you.